So moving on to part 4, we are on step 4 actually of our journey, and we have seen that we were able to identify and create the cost function, and we are able to identify and model the inequality constraints. So we are effectively here where we are trying to format both of these constraints in a form that our solver, in this case, will be able to understand. So we have already discussed that actually our solver would want us to have a cost vector, an inequality vector, the lower bound, higher bound, as well as this part as well, which is the matrix for the inequality constraint. So these ones go together for the inequality constraint. So in fact we have just discussed how we came about the cost vector f, and now how we are going to write that cost vector f in MATLAB. We've just talked about that. So moving on, we now look at the variable bounds. So the variable bounds, so basically we have looked at this f. We are left with a, b, lb, and ub. So we are going to be looking at, now we start with the variable bounds ub and lb. So in fact we said this would then come from this equation where we are limiting our f of I, which is effectively, according to MATLAB, this is going to be the x that we are looking for, the unknown. So if you look at this equation, it says the feed rate has to be between 0 and f max, which then translates to, for each and every hour, so if you have x for hour 1, 2, 3, up to 24, then the lower bound for each of those x's will be 0, which means now we have a 0 vector, which is 24 by 1 in terms of size. And then we have the upper bound will have to be f max. So here we have f max multiplied by a vector of 1s, all 24. So this is f max, f max, f max, f max, and so on and so forth. So then it means then our lower bound becomes that, the 0, and a vector of f maxes becomes our upper bound. So the way we write it in MATLAB is this. Then this becomes our lower bound, a vector of zeros, which is 24 by 1. So 24 by 1. And then we also write the vector of 1s, which is 24 by 1 times f max, so that we have a vector of f maxes. Done. So then we move on to the bigger part, slightly more complex than the others, which is the inequality constraint. So we are on this part now. We are trying to set this part. So now, from our model, we discover that we have these two equations which we have to compress to write in that form. So this equation, so the first one says the amount of material in the silo has to be between the minimum and the maximum. And then the other one says the material in the silo at hour I has to be equal to the material in the silo that was in the silo in the previous hour plus what's coming in from the belt conveyor minus what's going out to supply the plant, which is basically rational, right? And now we can see that it therefore means, if you look at this first equation, this one, therefore means then we can break this into two inequalities. That I has to be less than the maximum, and it also has to be greater than the minimum. So we can put it with the same less or equal to sign this way by multiplying it by -1 on both sides. So the reason why we do this is because we are looking at this sign here. The sign here is like this, less than or equal. So we are trying to put these two inequalities as in the same format, basically. So, but we have also realized that there's this linkage between the input and output to the amount of material in the storage. So, in our attempt We shall first try and therefore to create a general formula for the quantity of material in the storage. We'll see then from this equation it means that material at the hour S1 will be equal to the initial material, which will be given with the problem that we start off with at 12 p.m. in the morning, plus the material that comes in during that hour minus the material that goes out during that hour, and so on and so forth. In the second hour, it will be the material that's in as well as material that was there previously, so this should be S1 plus F2 minus D2. In the same way, we'll have S3 being equal to S2 plus F3 minus D3, right? And so on and so forth up to S24. In fact, if we use back substitution, because we can see that in this case here, this equation we can substitute into this other equation, the value of S1. In fact, if you do that, then we can have S2 in terms of S0 and F1 and D1. Remember this D1 and D2 that was going to be given, as well as S0 is going to be given. So we can in fact create or write the amount of material at any time S1 all the way up to S24 in terms of the inputs, the control inputs, as well as the demand and the initial storage. The initial value of the storage. So the only unknown in this case would be our schedule. In this case, it would just be under schedule because this is going to be given and this as well is going to be given. So generally we can write this that the amount of material at our SK is going to be S0 plus all the feed rate up to the hour K minus all the demands up to the hour K. Now, this then translates to, so this is the equation that we have. So you've just discovered that these three equations, we can translate them into that. In fact, this particular one can translate it into that. Therefore, it means that we can write a vector equation that S1 should be equal to S0 plus a lower triangular matrix multiplied by F1, sorry, a matrix of inputs F minus a lower triangular matrix of 1 times all the demand inputs. So we can write it this way. So in fact, if we denote a lower triangular matrices of 1 as trill dash 1, and we denote di as di with a bar as a vector of, so this one as a vector of input of the demands that we are going to know, then we can write these two equations, we can rewrite them this way, because we know that SI has to be less than 50, 40, and minus SI has to be less than negative 90. So we can write it this way. So in fact, we can write these two equations. We can rearrange this equation. We can rearrange this equation so that the only unknown this side is X, as in this form. So here you see the only unknown is X, and multiplied by some matrix A will be less than B. So we can rearrange this equation. We can just say minus S0 on both sides. To bring that S0 side, we can say minus, so plus this term to bring it this side. So we can rearrange it into this new form, and therefore it means this stack of lower triangular matrices will map to A, and this stack of vectors will map to B. So now we have got our A matrix as well as the B vector. Okay, so now that we've translated our constraints into the format that the solver can be able to understand, then we need to write it in MATLAB language, right? So we write it in MATLAB language. So in MATLAB language, the way we write it is, first of all, we need to be given the demands. So these are the demands which I have plot, which we have initially looked at in the form of a plot, and this is the initial amount. So the minimum amount of storage will be initial. So now here we first create a lower triangular matrices of ones, which is 24 by 24. So this is how you do it in MATLAB. And then therefore it means A will be equal to a stack of two lower triangular matrices, the one on top and the other one which is negative, as seen here. So it will be the one on top and the other one which is negative. So this one. So the one on top and the other one which is negative. So we have created A. For B, we need to create these two. So the first one is 5040 minus S0 plus the triangular matrix times the vector D. So this is 5040 minus S0 plus the triangular vector times D bar. So this D bar, I have put a transpose here because the way I've written my D bar here, it's in a form of a row vector, but we need it in a column vector here so that it can be able to multiply that. So it means the top of B will be like that, and the bottom will simply follow this equation as well. It will simply follow that. So then we'll have minus 1960 plus S0 minus the triangular times D bar. So D bar prime in this case, the transpose of that, because this was it was a row vector.